In section 116, we're going to look at piecewise linear functions. Piecewise functions are functions that are composed of separate pieces. So a function that had pieces like this would be piecewise function, where it's piecewise linear. There's a linear segment followed by a linear segment that goes in a different direction, followed by another linear segment. The pieces don't need to connect necessarily, so I could actually add another piece down here as long as I had one closed circle, one open circle to indicate that the function stopped at this point, continued from but not at this point, and went on. So connected or not connected, either way, but piecewise linear function, every segment of this function is going to be linear, but there'll be more than one piece. Okay, so our goals are to graph some piecewise linear functions, to write some piecewise linear functions, and then also to talk about absolute value functions as they relate to piecewise linear functions. In the first scenario, we have a situation, let's see, according to federal overtime pay law, your overtime pay is extra compensation above 40 hours per week, and we make 1.5 times the regular rate pay and a half for any hours worked in excess of 40 hours per week. So if we work a regular hourly rate of $9 per hour, what is your overtime rate? So $9 times 1.5 would give you $12. We can calculate that over here just to check. 9 times 1.5 is $13.5. So because it's $13.5, I made a mistake on my calculation. So if I made $9, I would make, like I said, $13.5 per hour. If my regular rate was $14 per hour in the next one, let's just go ahead and calculate that one as well. 14 times 1.5 would give us, this one should be 21. Oh, good, it is. $21 for our overtime rate. All right, so now we're going to assume that our hourly pay rate is $12 per hour. So if it's $12 per hour, I'm going to calculate the overtime rate right here. That should be half of 12 is 6, so that should be $18. Okay, and you can double check that. 12 times 1.5 should be 18. And now we're going to assume that we're making $12 per hour and we're working for a variety of hours. Okay, so if I work for 25 hours at $12 per hour, how much do I make? This is going to be 25 times 12. I would make $300. If I work for 35 hours instead, okay, I make $420. Now, I'm just multiplying these by 12 because that's my hourly rate. I'm not making overtime pay when I work under 40 hours. When I get into the 45, though, I'm going to have to make overtime for this. So for the 45, we're going to have to calculate that with, I'm actually going to make $12 for the first 40 hours. Then I'm going to make $18 for the next 5 hours, right? Because 45 hours. I make my regular rate for the first 40 hours, and I only make overtime rate for the amount that I am over 40 hours. And since I'm over by 5 hours, we'll make it for 5. So we have 12 times 40 plus $18 per hour, the overtime rate for those 5 additional hours. So we get to make $570. So we can see here that the way that we computed the values when I worked under 40 hours was different from the way I computed the values when I worked more than 40 hours. All right, so is gross pay a function of the number of hours? Is it a function? It is. Yes, it is a function because for each number of hours worked, there's one correct gross pay. So for each input, hours worked, there is one unique output. That's just the definition of a function. And it's true. Now, it's not computed the same way, depending if I'm working a regular shift or if I'm working overtime. It's not computed the same way, but there is still one procedure. I know how to compute it for under 40 hours, and I know how to compute it for over 40 hours. So again, the method is different. The method used to compute the pay is different, but it is a function because there is a method depending on what the input is. And that's going to be our first example of a piecewise function. I have to compute the pay differently depending on the input. All right, so we're going to write our equation for this function. If we have less than or equal to 40 hours, then my pay is, if I'm working regular time, not overtime, less than 40 hours, my pay is 12 times the number of hours. And so I use this function if I work between 0 hours and 40 hours. So those are supposed to both be inclusive. This equal bar got a little close to the inequality, so it kind of blended. So I'm going to emphasize it. They both have the equal bar because I could work 0 hours and 0 times 12 is 0, so I'd make $0. I could work 40 hours and I don't make overtime pay, and so I would have 12 times 40. Now, if I work more than 40 hours, well, if I work more than 40 hours, I'm going to make 12 times 40 plus I'm going to make 18 for just the amount of hours that I am over 40. So the H variable, it has to be, in this case, some number over 40. I know I'm making $12 per hour for 40 hours. I'm just going to make $18 for the number of hours that we are over 40. So if this was 45, 45 minus 40 is 5 more hours. So I'm working H minus 40 hours at the $18 rate. And I'm only going to use this function if my number of hours is larger than 40. Okay. So together, this forms our piecewise function. And as you can see, they have it written down for us right here. The only thing that they have done is they have gone ahead and simplified 12 times 40 as this 480 right here. And a piecewise function has this little curly bracket in the front. It actually doesn't close on the other side. It's just on one side of it in the front next to the function's name. F of h equals the bracket groups the two pieces of the function together. And we'll see that we have the first function, comma, its condition. We use this function if h is between 0 and 40. And we have the second function over its condition when h is larger than 40. Okay, use the piecewise function to verify the results from 2a. Okay, you can check this on your own, but if you plug in 25 into this function, since it's in between 0 and 40, 12 times 25 is 300. You plug in 35 into the function, it's between 0 and 40, so you're going to select this piece. And 12 times 35 is 420. And 45, since 45 is larger than 40, you're going to plug it in here. If you take 480 plus 18 times 45 minus 40, it's going to come up at your 570. So you're welcome to check those. Now we want to graph the gross pay function. All right. So when I graph the gross pay function, I'm going to use Desmos to make my graph. Let me get my Desmos window back up over here. And I'm going to go ahead and type them both as I originally wrote them, with P equals 12H and P equals, the 480 is fine. The 480 is our 12 times 40 plus our 18 times H minus 40. Now we are going to put the boundaries at the end of this function. I'm going to rescale this real quick first because I know the output on this is bigger than 480. And I know my input needs to be working more than 40 hours. I'm going to take it up to 60 for the input. I'm going to take my output up to 600. And that'll give us maybe even 700 or 800 just because I'm noticing that I'm not quite high enough. Now that I'm over here, I'm high enough. So if I graph these full functions, it looks like I have some intersecting lines. That's not what I want. So I do need to put the conditions on, just like when we did restricted domains for that box problem. So we're kind of practicing ahead for this. We're going to use the curly brace for the restriction. The first one, 0 is less than or equal to h, less than or equal to 40. Close your curly brace. So now it only graphs that line over the first chunk where we go from 0 to 40. And then the second one, curly brace. And then h is larger than 40, close your curly brace. And now the second function's graphed starting at 40, and then it continues onward. I'm going to change the color of these so that they're the same color. So it looks like one connected function here. I made them both, it's blue, but they're both the same color regardless, so that they together form this piecewise function. Now I can zoom out. So I see that I have a slope of 12, and then over here, the slope gets steeper, the slope of 18, and I'm meeting right here at that 40 point where they switch from one pay rate to the next pay rate. Okay, so that's what our function looks like. Okay, so on the next page, we get to try this again. I'll draw a rough sketch of our graph right here. It was like this and this. Okay, that's what we saw for the pay. All right, the next one, solid waste. So we're in a new scenario. Solid waste is charging a tipping fee for waste disposal. There's a minimum charge of $14.70 for up to 280 pounds of waste. If you're over 280 pounds, then it's $50 per ton. Note the $50 rate only applies to the amount of waste above 280 pounds. Right. So one of the things I note right away is that $50 is per ton. The rest of this is per pound. So we got to get our units to match. So we're going to convert the $50 per ton into charge per pound. So we got to convert the pounds into tons. So this is $50 per ton. So per is our division word, per ton. So we'll put ton in the bottom right there. And then 1 ton, we want these to cancel, so we want ton on top to cancel the ton on bottom, is equal to 2,000 pounds. And if we cancel ton and I take 50 and I divide it by 2,000 pounds, my units will be in dollars per pound. So I'm going to grab my decimals tool and do 50 divided by 2,000 to get 0.025 dollars per pound. So I had to keep that number up so I could see it while I was writing in my book. But our 50 divided by 2,000, $50 divided by 2,000 pounds is $0.25 per pound, or 2.5 cents per pound. All right, so complete this table. So there's a minimum charge of $14.70 for up to 200 pounds. So if I'm below 280 pounds, I'm not charged per pound. I'm charged just $14.70. So for 100, I'm charged $14.70. And I'm still charged $14.70 for 200 pounds. That's the minimum charge. I'm going to be charged that regardless until I hit the 280 pound limit. When I get to 400, then I still have to pay that minimum charge. And I have a additional charge for the number of pounds that we are above 280. So for the 400 one right here, I've got to pay the $14.70 plus I've got to pay the 0.025 dollars for just the amount of pounds that we are above 280. So 400 is 120 pounds more than 280. So that's going to allow us to calculate the amount for 400. All right, so back over into our decimals window, we're going to take our 1470 and we're going to add on 0.025 times, we said 120. And just to confirm that number, that was our 400 minus our 280. That's why the 120 came from. So the 400, we have, oops, too far. We have our $17.70. Okay, so this should seem reasonable. It's a few dollars extra to remove 400 pounds. We're going to do the same thing for the 600. We can go ahead and figure out how many pounds over 280 we are. We're 320 pounds over. So we're going to be charged $14.70 plus 0.025 times 320 pounds. And so this one's going to cost $22.70. All right. So again, we have two different ways that we computed the values, the cost values here, depending on if we were above or below the 280-pound limit. So we're going to write our function. So first, the function for less than 280 pounds. So for less than 280 pounds, our cost is $14.70 for any weight that is less than or equal to 280 pounds. It was just a flat fee. That's the minimum owed. It's always $14.70. Then, if we're above, we have to take our $14.70 and add on 0. Keep forgetting that 0 there, 0.025 times the amount that we have exceeded the 280 by. So our difference between our weight and 280. That's how we calculated the 120 and the 320 for this one. Is we took our weight, we subtracted off the 280, and we're going to use this if the weight is larger than 280. Now we're going to put those two pieces together for the function to write the piecewise function. So I'm going to have one function, f of w equals curly brace. The function is going to be equal to 1470 for w values less than or equal to 280. And it's going to be equal to 1470 plus 0.025 times w minus 280 for w values larger than 280. So if I were to write this out again, I might scooch this over just so our two conditions line up. It took me a little longer to write all that than I was expecting. So that's what we would have for our function, the two conditions, the two functions, and what their conditions are. All right, so sketch a graph. So back over to Desmos to draw my graph. Okay, I'm just going to turn these two off. I'm not getting rid of them, but turning those off. And I'm going to zoom home and I'll rescale this in a second. Now, this function, I'm going to start with f of w equals 1470. And our condition for this was that w has to be less than or equal to 280. And the second one, f of w, is going to be equal to 1470 plus 0.025 times w minus 280, and we're going to use that on the condition that w is greater than 280. So I can expand this for just a moment so that we can see our functions there, make sure that they're entered correctly, and then we're going to look at the graph part of it next. So let me actually slide this off to the side, see if I can expand the graph part a little bit. Okay, so I can't see anything yet. If I scroll up a little bit, I'll be able to see the 1470 bit. And I know that I have to get all the way on the x independent variable axis, the w axis, to 280 before I can see any change. So I'm going to take this above 280. If I put it right at 280, the change would happen right at the corner of my window. So let's just go like 500. Okay. Oops, I didn't mean 5,000. I put an extra 0 there on accident. All right. And so now I can see the change right here, and I could rescale the y manually, but I can see this pretty well right now, that we're flat at the 1470, and then at, this must be where 280 pounds is, we start taking off in the upward direction as we are paying for the waste removal above 280 pounds. Okay, so that is what our function looks like, and I could draw a really rough sketch of it. It's flat at the 1470 and then that slow increase. And if I put some scale or axes to this part of change is the 280, and that's our 1470 on y. And again, if you wanted to have more ordered pairs, if you could get them from the graph or from the table that we've made. Okay, just a sketch is a real rough graph to see the shape. Okay, we have one more chance to, I think one more. Okay, yeah. One more it looks like to do this commission example to set up another set of piecewise functions. All right. So an incentive to attain more sales, a salesperson is often paid on commission. The commission scheme is the accumulative plateau method. Using this method, a salesperson is paid a commission at a greater rate for a greater level of sales. In a particular company, we get 5% on sales up to 10,000, 7.5% on the next 10,000, and 10% on all sales that are over 20,000. Okay. So, for example, the commission on $8,000 would be 5% because we're less than $10,000. $12,000, we're going to make the 5% on the first $10,000, and then we're going to make the 7.5% just on the amount over. So on the next $2,000, get to $12,000, and so on. All right. So how much will our salesperson earn on $6,000 in sales? So that's under 10,000. So I'm going to take the 0.05 times 6,000 to get the commission here. I'm going to go ahead and make a new window, and we'll compute our multiplication. So, oops, I hit the wrong key, but we're going to make $300. All right, let me pull my screen up a little bit. I don't think I need my graph to be so wide anymore. Keep my Desmos window up here. How much will the salesperson make on $15,000? Okay, so I know they're making 0.05 for the first $10,000. And they're going to make the next higher rate, the 7.5% or 0.075 on 5,000 because they are over 10,000 by 5,000. Okay, so this will give us 0.05 times 10,000 plus 0.075 times 5,000. Okay, so they would make $875. Okay, so now on 24,000. All right, so on 24,000, they're going to make 5% on the first 10,000 plus 7.5% on the next 10,000. That gets them to 20,000. Once they're over, so the next $10,000, once they're over 20,000, they're going to make 10%. On there's 4,000 that are over 20,000, so on the last 4,000. Okay, so 0.05 times 10,000 plus 0.075 times 10,000 plus 10% times 4,000. Okay, so they make $1,650 for the $24,000 in sales. Okay, is the commission earned an amount a function? Yes, it's a function because you get one exact output for each input. Where each input corresponds to exactly one output. It might be a different process used to compute them, but there's only one answer. There's not a, well, maybe they made 1650 or maybe they made 8,700. I don't know. There's not two answers. There's just one answer. They made 1,650. Different processes depending on how much money, but there is a process no matter what. So I can figure out how much they made with one answer. Okay, so in number 9, it looks like on this page and the next, we're going to try to build up this function. So first, I'm going to keep my decimals up there. Hopefully it's not in the way because I'm going to need it in a moment. So first, we're going to do our C, the commission as a function of S sales, if my amount is less than 10,000. So if we are less than 10,000, like part A, we just need the 5% times our sales. And that's going to be true for any sales that are less than or equal 10,000. Okay. Now, on to the next page for the next part of the function. For the next part of the function, I'm going to make the 0.5% for the first 10,000, and I'm going to make 7.5% for the next however much it is. So the first thing I actually want to know is what is 0.5 times 10,000? Because that amount right there, that amount is going to be constant in this function. I'm always going to be over 10,000, so I'm always going to make the $500, then plus more dollars depending on how high above 10,000 I am. So I'm going to keep that going on to our next page here. Okay, so C of S, if we're over 10,000 but still less than 20,000, we're going to be making $500. And again, that $500 is the 0.05 times 10,000. Plus, we're going to be making our 7.5% on the amount of our sale that is larger than 10,000. And the condition on this is going to be if S is larger than 10,000, but less than or equal to 20,000. I'm going to sneak it on the next page. Okay, didn't have room on that page. All right, so we're going to do this again here. C of S. All right, so like before, I have to calculate 5% times 10,000 plus 7.5% times the next 10,000 just to get me to 20,000. Then the amount that's over 20,000. So those two are fixed. So I'm going to add, might as well add it onto this line. I'm going to add the 0.75 times the next 10,000, getting us to 20,000. So I'm going to make 1,250 from this chunk of it, plus the additional amount for the amount over 10,000 that we are. Okay. All right, so we have our, I lost my number, our 1,250. I have my 1,250 plus the 10% times however far beyond the 20,000 we've gone, so S minus 20,000, and we use this function for S's that are greater than 20,000. Okay, now I can hide my decimals. All right, so we're going to put all of these pieces together to make one lovely piecewise function here. C of S equals, the first function was 0.05 S. I'm going to write the conditions after I have my functions so I know about how far to space them out. Then I'm going to try to write this one a little smaller, 500 plus 0.075 S minus 10,000, and 1,250 plus 0.10 times S minus 20,000. The condition on the first one is that S is less than or equal to 10,000. The next one, S has to be strictly larger than 10,000 but less than or equal to 20,000. And the last one is for S's that are larger than 20,000. Notice in your border values that you can be less than or equal to 10,000. You have the equal bar on this one. It means you cannot have the equal bar on this one because 10,000 has to be clearly in one of the two groups. Technically, it doesn't matter which of the groups because these functions connect. If you put 10,000 in here, 10,000 minus 10,000 is 0. You're going to get 500 just as you would get if you put 10,000 up here. But it only can be connected to one of the pieces, whichever one makes sense. It tells us specifically that we use this function less than or equal to 10,000. So we're going to put our equal bar here. It cannot be here. Same thing over here. Equal to 20,000 in this function. No equal bar in the next function because we don't want both of them to be true or it would not be a function. We might have to have a function where we have a clear defined boundary, a clear defined piece for each of the pieces. Okay. All right, so I'm going to use decimals to help to make sure my function works here. Okay, so I got to type in my functions. So C of S equals 0.05 s, we're going to use this piece if s is less than or equal to 10,000. Okay, c of s equals 500 plus 0.075 times s minus 10,000. Use that function when 10,000 is less than s is less than or equal to 20,000. And last, our 1250 plus 0.10 times s minus 20,000, using that function when s is greater than 20,000. Okay. Now, I want to use these functions to evaluate. Right now, they are all graphed, and I might as well just look at the graph. So I'm gonna rescale this real quick and look at the graph. I'm gonna talk about evaluating in just a second. I need my inputs to be quite large because my inputs are going above 20,000. So I'm going to take my x-axis for the inputs and make 30,000 very large inputs so that 24,000 is not going to be too close to the edge. And then my outputs. So I know right here at 20,000, I'm at 1,250 or 1,250. So my outputs have to be not up to 30,000, but they have to be above 1,250. So let's just go for 3,000. Close my graph settings, and you can see the three pieces. So the first piece, there's a change right here, gets a little steeper. There's a change right here, gets a little steeper again. Right now mine are in 3 different colors, so I can see that this first segment is red. It helps me identify the next segment is blue, the next segment is green. It helps me identify the break. But you can also, if I click on one of them, the middle one gets bolder. You might be able to see that bolder right here piece to see the difference between each of these 3 segments. So you can see where it connects to the next one if the connection point was hard to see because of the colors. All right, so I can see the graph just fine like this, but the problem becomes I can't do the function evaluation c of 6,000 because I have 3 functions labeled c here. So what I can do is label them c sub 1, c sub 2, and c sub 3. And so I can tell it which function to plug the value into. That's the only way for me to be able to use function evaluation. When I have the same function name used more than once, it will not be able to use function evaluation. But I can get it to evaluate by just naming them something slightly different. So C1, C2, C3. So I can evaluate 6,000 into the first function. We're going to make $300. 16,000. Now it's not going to go into the first function, right? Undefined. It's going to go into the second function. So 16,000 goes into the second function, and we would make $950. And then 24,000 again won't go into the second function because it's too big. It'll only go into the third function because it meets the criteria for the third function. So their commission would be $1,650. Okay, so that would be one way to get Desmos to evaluate it without having to retype them individually. You could, of course, retype them individually like we had done before to calculate them, but they wanted us to use the function, make sure the function was working. So we can do that with the little subscripts and knowing which function piece to use based on the condition. Since 24,000 is bigger than 20,000, it's got to go into C3, and it won't even work in the other ones, right? Oops, I didn't mean to get rid of C, I meant to get rid of the number. Won't even work in the other ones. So had we tried C1 or C2, it doesn't work because it didn't meet the condition for that function. Okay, so a quick little sketch. So this one had a lower slope, a slightly higher slope, and a slightly higher slope for the end. And each of these little imaginary breaks that I made here, that was 10,000, and then that was 20,000. Right. Almost done. We're done with the piecewise function piece. Now we're going to look at the absolute value function as it pertains to piecewise functions. So consider this function f of x equals negative x if x is less than 0, if x if x is greater than 0. What is the domain? All right, so we use this function for anything that is less than 0, and we use this function for anything that's greater than 0 or equal to 0. So everything is going to fit into one or the other of those, so it's all real numbers. Or in interval notation, the interval from negative infinity to infinity. Complete the following table. All right. So our function is f of x equals negative x if x is less than 0, and x if x is greater or equal to 0. So if we're less than 0, like negative 4, we'll do negative x. So negative 4 is 4, negative 3 is 3, negative 2 is 2, negative 1 is 1. And then I can't use the top function anymore because I hit 0, and that's in the second condition. So if I plug 0 in, 0 is 0, 1 is 1, 2 is 2, 3 is 3, 4 is 4. Sketch the graph. Okay, it wants me to just sketch it real fast, so I'm going to put in some axes right here and then sketch my ordered pairs. So negative 4, 4, 1, 2, 3, 4, 1, 2, 3, 4, negative 3, 3, negative 2, 2, negative 1, 1, 0, 0, 1, 1, 2, 2, 3, 3, 4, 4. Now, you could have plugged in decimal values to this function. You could have plugged in other values to this function. So in the by hand sketch, we're going to connect these, and it is a pointy V-shaped graph. Shape is a V. So if I describe the shape, it is a V shape, not a U shape, which would have a curved bottom. There's a V point shape down here. As we connect down, hit 0, and abruptly turn around. Okay, what is the range? Range is outputs. So where did domain the other side? Range is outputs. We have 0 being the lowest output. There are no negative outputs. 0 is the lowest output. And then the outputs go up to infinity. So we would bracket include the 0 because we do hit it. We would go up to infinity. Now, I forgot it asked me to use my calculator to verify the graph. So I'm going to go back and do that now. Get rid of my cost stuff. And we can type this one in two pieces. So the first piece was negative x for the condition x less than 0. And then we're going to use positive x for the condition x greater or equal to 0. There's our V-shaped graph composed of those two partial segments there. Okay, so that shape of that function, it says may seem familiar. It's also the same thing as the absolute value function, f of x equals absolute value of x. So if I graph that one as well, absolute value of x, it's graphing right on the same graph. If I make this one dashed or dotted, you can see that it graphs right over where the other graph was. You can see the dot showing up on your lines. You can click it on. Oops, let me do done first. Click it on, click it off, and you can see your dot show up in the same place. The absolute value function is one function that contains those two pieces. So the absolute value function can be written as a piecewise function with the negative x and positive x functions under those different conditions. All right, over to the bottom of our page. How does the graph compare? So they were the same graph we had. And then, again, they wanted us to graph the absolute value function. We did so and see how it compares. So it's the same graph. So if I did graph, again, if you want to check this one, graph the absolute value of x minus 2, or the function in two pieces, negative x minus 2 for the condition x minus 2 is less than 0, and so on. The x minus 2 for the condition x minus 2 is greater than 0. So you can check that. Those are the same, but they're trying to illustrate that the absolute value function can be separated into a piecewise function. Okay, so use the piecewise function for g to evaluate each of these. So the piecewise function for g is written right above. And so if g needs 0 as an input, 0 is less than 2. So it's going to use the first condition. Negative 0 plus 2, that's 2. All right. If I put in 5, that would fall into the bottom condition. 5 is greater or equal to 2, so 5 minus 2, that's 3. If I put in 2, 2 is not less than 2. It is greater or equal to 2. The equal bar is in the bottom one, so 2 meets the bottom condition, and 2 minus 2 is 0. So that's how I would evaluate the piecewise function for each of those. We're going to make a graph on the other side. Now, just want to note before I go to the other side that I also could evaluate in the original function. If I did g of 0 here, the absolute value of 0 minus 2 is the absolute value of -2, and the absolute value of -2 is 2. So we're getting the same thing by using the absolute value function as we do with the piecewise function. So trying to show that they're the same and that piecewise functions can be used to compute absolute value functions and maybe make it even a more clear choice of how to evaluate it and not have to worry about the absolute value symbol and how that operation works, taking away the negative sign when there is one. Okay. So we're going to graph this function and describe how the graph can be obtained from that graph. Okay, so I'm going to get my decimals back up. So I'm going to leave this one up for, let me just hide it for a second. We're going to graph our g of x function equals the absolute value. This key is like right above my enter key. It's like a vertical bar for absolute value. X minus 2, vertical bar. It's next to the bracket symbol. Okay, so that's my sketch. My V shape. There we go. Just drawing my little V shape there. And then I describe how the graph of this one can be obtained from the graph of this one. So the idea that we were looking for here is that they're the same shape. It's just going to slide it over to. So we're going to shift it to the left. I'm sorry, I don't on my right and left apparently. Shift the original graph, which was the absolute value of x, to the right by 2 units. So shift the absolute value of x 2 units right. To get the absolute value of x minus 2. And it's 2 units because 2 is the value in the inside, and also because you can click and see that you went from a base of 0 to a base of 2, so it's 2 units over, but the 2 does come from the 2 in the function.